Hello. I'm sure that most of you are familiar with services for storing files. You may know or have heard of Dropbox, Google Drive, or iCloud. These services allow us to store our files, access them from different devices, and share them with other people. Let's try to design service like this. First, let's consider how our application should look and what features it should have. Then we will discuss possible requirements with our imaginary interviewer. The first question is, what are our references? We can look to products like Dropbox, Google Drive, Amazon Cloud Drive, and Apple iCloud, and others. We understand that the primary feature of our application is file storage. We need to determine how users can add new files, browse, and manage them. We assume that our application will consist of a main screen where we display stored files and provide controls for adding and other features in the header. Features like searching or sorting are essential even for the MVP or minimal viable product. Users simply can't use our application effectively without search, especially if they have more than 100 files. So all these features should be available from the start. Now we have a general understanding of what our application should be. So it's time to ask the interviewer some clarifying questions. Remember that it's always better to ask the interviewer for guidance on how the application should look, especially if you are not familiar with similar applications, rather than attempting to answer the wrong question. The first question is what we should design, frontend or frontend and backend parts? And the answer is we should design frontend and API parts. The next question is, do we have to support file sharing? Yes, users can share files with other users and should be able to view files that other people have shared with them. Should we support some offline features? Yes, users can download saved files. It means that users can mark files as available offline and later, when connection is lost, they can download this file. When a user adds or deletes a file on the device, do we need to update its status on other devices? For example, if a user has added a new file on the desktop, it should also update on mobile and other devices as well. It means that the state of the files should be synchronized between devices. What languages should we support? English by default and any other languages in the future. If the interviewer said that we can leave the backend part out of the scope, it doesn't mean that we will not face some general backend questions. For example, the interviewer may ask us how we want to store files or how we can improve the loading speed for users. Also, the basic knowledge about backend side may help us to make front-end design better. So now we are ready to collect requirements. Let's start with functional requirements. Users should be able to add files, share them with other people, browse, sort, and search by files. Non-functional requirements includes accessibility, performance, localization, offline mode, and security. Once we have covered these aspects, we need to ensure that we're on the same page with the interviewer. So it's a good time to ask them if our list of requirements is okay. Let's look at the schema or high-level architecture of components. We start with a classic MVC structure. The model will be represented by two parts, client store and responses cache. It is important to distinguish these two types of stores. The client store is usable for storing client-only data. That may include input values sorting parameters, or, for example, the last scroll position. In other words, everything that we will not receive from the server and shouldn't synchronize or send to it. Responses cache is a store for server responses. In 2 words, client store saves mutable data, client-only mutable data, whereas responses cache are usually immutable and is used for saving responses from the server. The controller is a core of our application. It's responsible for connecting view and model. The view doesn't fetch data directly from the model or server. The view does that through the controller. The same is true for writing data. The view doesn't put data directly into the model. Instead, the controller handles view's events. The view is responsible only for displaying data, so it's UI layer. It receives data from the controller and sends user events to it. Separation by layers gives us a reliable and clean architecture. We can make changes in one layer and be sure that we will not break something in another part. We have discussed the main parts. Let's look at others. We allocated the API model into a separate layer. The difference between the main controller and the API model is that the API model is responsible only for handling network requests. Everything connected with the server should be here. In other words, the controller should work with the API model as if it doesn't know that the server exists. For example, if the API model receives a server error, it can prepare it and send appropriate form to the controller. The next thing is a server. We don't want to go deep into backend details. However, it might be wise to describe the backend side in general terms, because it might be useful for us in the future when we will discuss file uploading. The backend side will consist of 4 main parts: app server, relation database, file storage, and CDN servers. The app server is responsible for communication between the frontend and databases. The app server keeps business logic. When a user adds or deletes a file, it's the work of the app server to handle this event. For storing metadata, we will use a relation DB. Metadata is information about the files, users, and other entities. For example, each file should have a name, description, owner, and a link to download. All of these fields are metadata. In other words, metadata is everything that is not a binary file, in our case. A relation DB is a good choice for it because entities may have relations. Let me explain. For example, one user may have many files, and one file may have many users with whom the file was shared. The relation like this is called many-to-many, or one-to-many, or many-to-one. For storing binary files, we will use file storage. To deliver files to the users faster, we will add CDN servers, which will be located closer to the users in different countries. Let's take a closer look at big components details. Discussing component details shows the interviewer that you are aware of the composition of components. Our application will consist of 3 main parts: header, files, and context menu. Header includes features that are available for our table. For example, search, adding files, and table controls like sorting and changing view models. Files is a grid of files or representation of users' files. It may be in two different views, table view or list view. The file item is the smallest unit of our grid. It might be folder or file. Context menu is a list of available features for a particular file or folder. For example, rename file or delete it or move to the folder. The menu is usually available by clicking on the right mouse button. So next, let's look at the UI. Usually you shouldn't draw the UI during the interview, but I did this because it might be useful for our purposes. Because keeping the whole picture of how the UI looks may help us better design the application. So there are two screens, main screen and the same screen but with different view. So on the left side it's a table view, on the right side is a list view. The table view is default mode. The next question is how we should render the application. There are three main options: client-side rendering, server-side rendering, and hydration. Hydration is a combination of both approaches. Before we select some particular approach, we have to decide what is important for us. We expect that main page is highly interactive and it should work fast. SEO is not important. Content on the page shouldn't be scanned by SEO engines. Fast loading is desirable but not crucial. Should work well on all types of devices. Let's look at the comparison of all approaches. On the left side, we can see requirements. I highlight them by different colors in order to show what is more important for us. As we can see, we expect that our application will work well on low performance devices, and also it should provide smooth interactions on our screen. Basically, we design on the main screen and it's like a single page application. After the look at this table, we can see that client-side rendering is more suitable for cases when we are developing a web application rather than a website. Google Calendar or Dropbox are single-page applications with high interactions. In other words, most of the user activities are happening on the same page. An example of a website is Amazon. We are moving between pages, and each page usually doesn't include many interactions. So, client-side rendering is a nice approach here. Yeah, that's true, but maybe we can do even better. And yeah, iteration is more suitable in our case. Iteration is a process of adding interactivity to the static HTML code. It means that for the initial loading, we load a pre-rendered page that was pre-rendered on the server and show it to the user. Because the page is rendered on the server, which is usually faster than the user's device, especially it's true for low performance mobile devices, and we don't need to load the whole JS bundle, we are able to show something to the user much faster. However, the page would not be interactive for some time. In other words, we have good first contentful paint and bad time to interactive. So we have a big gap between these two timestamps. A situation like this, when user can see something on the page but can't interact with it, is also called the uncanny valley effect. Such a problem may be solved by using a technique like progressive iteration. We will not go deeper here. There is much information on the internet. But during the real interview, the interviewer may ask you for more details. So if you consider hydration as an option, you should be prepared to talk about the trade-offs of this approach. For our case, we will use hydration. Client-side rendering also is a good choice, especially if resources of our team is limited. Client-side rendering is the cheapest way to build a single-page application, and it's also very popular. And it making it easy to find developers to work on our application. Now let's try to construct a data model for our application. We have two main entities, file and folder. Let's look at some interesting fields here. For example, file has two fields, have access and access requests. Have access is a list of user ideas that already have access to the file. Access requests is a list of user ideas that requested access to the file but still waiting. Number of revision is in other words, number of the version of the file. For example, if user uploaded a file and after that he wants to replace this file with a new version, the number of revision will be updated by 1. URL is a link to the downloaded file. In the folder type, we can see almost the same set of fields. It also has items. Items is a list of files or another folders. The next question is, where should we perform data manipulations? Data manipulations includes tasks such as sorting, filtering, and searching files. We have two options here. We can perform these tasks on the client or on the server side. Both approaches have their advantages and disadvantages. Before we choose one of them, we need to determine what is most important to us. We anticipate that our application should perform efficiently on all types of devices and be highly scalable. Data operations must remain fast regardless of the data size. Let's explore possible options. Performing these operations on the client side is straightforward and offers high flexibility. For example, we can easily add new types of filters on the front end without needing extensive interactions with the backend team. However, we can achieve better scalability and performance by implementing data manipulations on the server side. Consider a scenario where a user has a low-performance mobile phone. In this case, operation may be sluggish. Additionally, even powerful desktops can struggle with handling millions of data rows. On the other hand, if similar situations occurs on the backend side, we can easily add new servers to the server pool. However, the server-side solution is more costly and less flexible. It requires coordination between two teams, which may slow down the implementation of new features. Despite these trade-offs, the server-side solution is more suitable for our case. As you remember, we have been tasked with implementing not only the front-end side design, but also the API. So let's begin. We won't go deeper into straightforward tasks like deleting or getting files. Instead, let's focus on 3 non-trivial aspects: uploading files, downloading files, and sharing files. Before we begin doing an uploading file, we need to check if the file already exists. First of all, we need to send metadata to the server. This metadata should include the file name. If the server responds that a file with the same name already exists, we have 3 options. Replace the file. In this case, we need to upload the new file and increment its revision, for example, from 1 to 2. The second option is keep both files. In this case, we upload a new file but change its name, for example, file name 1. And the third option, we can simply cancel the uploading process. If the user chooses to continue uploading in the previous step, the server will return a file ID to the client. We will use post request for uploading a file when we assume it's a new one, so it's a new file. However, if we know the file will be replaced, we should use put. On the client side, we will use a native HTML5 form to provide an upload interface for users. We will send a request to the server with a form data object. So let's look at the whole process. First, we send file name and other metadata to the server. The next step is checking this metadata and personally checking file name. If it's okay, server write metadata to the database. Next, we return a file ID to the client, which we will use later to resume loading if it was interrupted for some reasons. The client receives the file ID and now it starts loading the file to the server. So the next step, server starting to save file to the file storage. As you remember, we use two different storages, RelationDB for metadata and file storage for binary data. The next possible step, if sending was interrupted, we know that we was stopped on the X byte, for example. Next, if the client restored the connection and want to continue loading, and as you remember, we already have a file ID, we can ask server from which byte we should start, and server by this file ID can return us the start byte. So when we received a start byte, we can continue loading from this byte. So the next step, server can continue loading our file to the file storage. Resumable upload should be optional. We don't need this complex approach for uploading small files. The threshold at which we should implement resumable upload depends on the quality of users' network connections. If we are targeting users in areas with poor internet connectivity, the threshold could be around 10 megabytes, for example. Otherwise, it might be around 100 megabytes. For resumable uploads, we can use the upload type resumable parameter, which we will send with our metadata. We should also implement file chunking on the backend side. As we will learn later, we will use the observer for processing content, for example, encryption and compression files. We can also use it for chunking files, which offers us several advantages. Chunks can be uploaded to the file storage in parallel, resulting in better performance. If uploading is interrupted, we can resume from the last uploaded chunk. If a file has small changes affecting only one or a few chunks, we can upload only those affected chunks. So let's look on the downloading file. Again, we have two storages, RelationDB and file storage. When we want to download a file, we need to obtain the file's path. So the first thing we have to do is to make request to the app server. The app server sends a request to the RelationDB, which returns metadata, including the file's path. Once the path is received on the client, we can initiate the file download from the file storage. Let's look on the file sharing. File sharing is relatively easy. We have two separated endpoints, one for files and one for folders. In both endpoints, we will pass the list of users' ideas to which we want to give an access. Before we go next, let's discuss what is access means in our case. In our case, it means only rights for reading files. We assume that for simplicity. This frees us from concerns about the synchronization. If two users have access to editing one file and they both replace it or change it at the same time, we will face a problem of concurrency. This is another significant topic, how to solve problems like this, which is completely out of scope. So let's look at the possible API for revoking access. We have two different options here. The first one is to use different endpoint. So we have a share files and also we have a revoke access. The next approach is to use the same endpoint but with a special variable revoke. The first approach is more intuitive, but we have to create an additional endpoint which increases the complexity of the API. So this approach is not really scalable. The second approach allows us to write less code, but it may lead to confusions, especially if the API is not well documented. So what is better in our case? Our choice is to use two different endpoints, one for sharing access and one to revoke. This way is the most straightforward, easy to implement, and easy to use. Okay, we have covered the high-level models, and now we're ready to dive into the details. First and the most important part is security. Let's discuss specific security issues and recommendations for our application. Later, we will discuss more general things. The first question is how we can protect our files. For example, if we put users' files to the storage and hackers, they will have access to the storage and they steal these files. So it means they can do with it files everything that they want. So we can use some tools to prevent this situation. For example, we can use encryption. Let's look how it works. Client send file to the server, and server, before saving these files to the file storage, ask the special model, which is called data encryption model, to encrypt this file, and only after that put this encrypted file to the file storage. The opposite scenario is decryption of files. Let's look how it works. First, user send request to the file to the server. Server send request to the file storage. File storage stores encrypted files. So again, we need a data encryption model to do an opposite operation, to decrypt file, and only after that send it to the server, and after that server can return the decrypted file to the client. The interviewer may ask us a question: what we will do if hacker tries to steal a file during its transfer between the client and the application server? Maybe we should use client-side encryption. The answer is no. We should avoid doing that on the client side for the following reasons. First, the web application or mobile application, something on the client side, may be easily hacked or manipulated. Next, encryption logic may vary across different platforms, so it's just harder to develop and maintain. And the next, it's not scalable because encryption, it's an operation that takes some resources. What else we can do to improve security of files? There are 4 pillars of security: files encryption, using security protocols for transmitting data between server and client and server and other servers, prevent unauthorized access, and testing for vulnerabilities. We discussed encryption earlier, so let's move to the next point. This one should be straightforward. We should use HTTPS instead of HTTP for transmitting files. Basically, we should use HTTPS for all requests. Next, we have to check access rights. If a user doesn't have access to a file, it shouldn't be visible to them, even if the user has a direct link to the file. The last point concerns how we can find potential vulnerabilities during the lifespan of the application. In other words, what should we do regularly to ensure that users' data is safe? The first point is data income. Where files is uploaded, we have to scan files for potentially malicious content. However, we shouldn't allow new files to get into the main storage before they are checked. So we have to isolate them within a sandboxes. This prevents potential malware from executing or affecting the host system. Next, we have to periodically scan the main storage with antivirus engines or specialized malware detection tools. This helps identify known malware signatures and detect potential threats before they reach users' devices. And the last one, we have to educate users. Provide clear guidelines and educational resources to help users understand potential risks associated with file sharing and the importance of maintaining good security practices. But interviewer may ask us, if we scan files, how can we keep them private? The short answer is we can't keep them totally private. Basically, we have two options. If we don't scan files, we run the risk of all users' files being stolen by hackers or corrupted. If we do scan, there is a potential risk of data escaping through antivirus engines or a malicious employee. The second option, in my opinion, is much better. But maybe there is another way how we can provide maximum privacy and security at the same time. The possible option here is to use peer-to-peer connection for users who need maximum privacy. Let's see how it works. Two users want to establish a peer-to-peer connection. User 1 sends a file to the server. The server saves only metadata about the file, but not the binary data. It saves metadata to the relation database. User 2 requests the file from the server. The server establishes a peer-to-peer connection for the users. Now we are ready to transit file from user 1 to user 2. This transiting is private and at the same time it's secure because we don't use common file storage. The next question is how we can synchronize files. As you remember, we have to implement file synchronization between different tabs in one browser or between different devices. We have three possible options here: push, pull, and visibility change event. Visibility change event will be called when user change the tab in the browser. However, it will not work if a user keeps the application open on two different devices at the same time, because both tabs are active and this event will not call. The next option is to use push or pull strategies. The pull strategy involves asking the server for updates, for instance, every 5 seconds. It's not very effective because file additions or removals are not very frequent operation. It is also called short or long polling. The next option is a WebSocket. However, we don't need a bidirectional channel, so a WebSocket which brings additional complexity is an overhead solution in our case. So we have only one option, server-side events. Server-side events is easier to implement and maintain because it uses the HTTP protocol. Server-side events is a good choice for rare events. It's our case. However, because of using HTTP, server-side events has a lot of HTTP overhead. But since file synchronization doesn't happen very often, it is acceptable in our case. So let's see how it will work in practice. In this diagram, the first instance, where there is another tab, device, or browser, sends the file to the server. Server saves it to the storage and then sends server events to all subscribers. Subscriber is another instance. It also may be tab or different device. The server knows from which instance the file was sent and can skip it. All other instances receive the server events and update the UI without force reloading the page. The next point is the type of connection we should use to upload and download files. What if the user switches to a mobile connection? This could result in unwanted traffic consumption. Firstly, this is not very important for us as we are developing a desktop version of the application. However, the users can use our application via the browser on mobile phones or install the application as a PWA. So if we find way to track it, we have two possible options here. We can ask users or we can just prevent downloading. We can warn the user about the possible traffic consumption and ask what we should do, continue the download or stop it. The next option is to just stop the download and continue it when a high-speed connection is established. So the first option is better. Let's look how it might work. User switched to the cellular network. If yes, we check the file size. If it's bigger than 100 megabytes, we ask user what we should do. If user clicks no, we stop downloading for now, and we continue it when user switched to the home network or Wi-Fi. We have already discussed file encryption. Let's see how else we can prepare files before saving them to the storage. Space on our servers is not free, so it would be a good idea to compress files before saving. Let's add a model for compressing as well. In reality, both modulus, compression and data encryption model may be allocated on the same server or they may be separated. It doesn't matter for our design. For simplicity, we consider it as a one server with two modulus. So now this model does two things. It encrypts our files and compresses them. The next big topic is an offline mode. What features should be available when users don't have an internet connection? Users should be able to mark files as available offline. Users can browsing downloaded files, and they can download these files. Service workers make interface available offline. Without it, we just can't show our application when users don't have internet connection. We can work service workers and cache API to save assets on the disk and redirect requests to the cache when the user is offline. Let's see how it works. Our application tries to get files from the server, but since there is no connection, the request fails. If we don't have a service worker, we just simply show 404 error. A service worker can intercept requests, and if the user is offline and assets are cached, redirect the request to the cache and return saved assets. But before assets appear in the cache, we have to save them into it. When the user opens the application for the first time, the service worker requests assets from the nearest CDN server. If the CDN can find files in the cache, it returns them. If not, it will get them from the web server for the first time. Now let's explore how users can make files available offline. First, users need to mark them. Then, our application starts downloading these files in the background with a low priority. This means that if a user starts downloading another file explicitly, we should pause the background downloading, prioritize the new file, and continue the previous one download later. Next, files are saved to the IndexedDB. IndexedDB is the only choice here. We can't use, for example, local storage because it has limited capacity. IndexedDB is fast, it supports binary files and offers relatively high capacity. The exact capacity varies depending on the browser. For instance, Chrome, the most popular browser, allows using up to 75% of the browser available space for each origin. Browser available space is typically around 80% of the disk's available space. For example, if a user has 100 gigabytes of space on the disk, we can utilize up to 60 gigabytes. The final step is that when users lose their connection, downloaded files remain available to them. The next topic to consider is internationalization. When discussing this topic, several factors come into play. First, we expect that all pages will be translated. Additionally, we should aim to automatically detect the user's language. However, we must allow users to change the language if they want. We should also consider right-to-left languages and review potential issues with long words. Regarding translation, we can use either a translation team or automation services, depending on our resources. JSON is a good format that's suitable for different situations. It's a human-readable and supported by most popular translation management systems, or TMS. Formats like ICU are more powerful. However, JSON is the best choice in our case. Language detection can be based on a combination of the accept language HTTP header and IP address, but users should always have the option to change it. Some countries have multiple languages, and users may use VPNs. When dealing with RTL languages, right to left, it's essential not only to change text direction, but also to adjust the positioning of interactive elements like carousels and icons. For example, if an icon was on the left side of the text, it should be moved to the right. Arabic glyphs are usually smaller and more complex, so adjusting font size may be necessary. Finally, we should test UI elements with long words in various languages, because a word that's short in one language can be very long in another. Pseudo-localization. It's a technique which uses a pseudo-language with deliberately complex glyphs and long words can be helpful for testing. Accessibility knowledge is crucial for web developers. Fortunately, accessibility requirements can be categorized into 4 main groups. The first and most important rule is to use semantic elements. For example, using a button element provides features like keyboard accessibility and keyboard events out of the box. The next point is to use appropriate area and role attributes. If for some reasons we can't use semantic elements, we should add correct area and role attributes to divs, spans, and other non-meaningful elements. Keyboard shortcuts can be useful for users who can't use mouse for some reasons or just prefer using the keyboard for efficiency. For instance, we can add a Ctrl or Command plus S shortcut to quickly share a file. Lastly, regarding image accessibility, while it may not be highly relevant for our application, if we include images, we must ensure that they have appropriate alternative text. Performance. Since our application is a relatively general single-page application, there are no special recommendations here. However, let's discuss basic rules for ensuring high performance. The first category is network performance, which focuses on reducing latency between the client and the server and minimizing the amount of traffic that users have to load. We will use CDNs to host data closer to users and reducing latency as a result. Additionally, where possible, we implement server-side rendering. For example, if a page is static, we can render it on the server, store it on a CDN, and deliver it to the client much faster. Lazy loading is beneficial not only for images and media content, but also for components that are not needed for initial loading, for example, pop-up windows and analytics scripts. We also implement caching for assets like JS, HTML, or CSS files by service workers and Cache API to ensure that assets are loaded only once. We also will use data compression and latest version of protocols like HTTP 2.0. We have covered everything at the network level, so now we can focus on improving performance at the interface side. Here, we should distinguish between real performance improvements and perceived performance improvements. For example, moving heavy computations from the client side to web workers or to the server represents a real performance improvement. On the other hand, adding skeletons may make the application appear to load faster, even though the actual loading time remains the same. Now let's explore what we can do. First, we can use infinity list and virtualization for long list of files. Next, we should avoid JS animations and heavy CSS animations. We should use skeletons and loaders, and use CSS naming convention, for example, BAM. Next, we take a closer look at virtualization. Initially, we display a limited number of files on the page. We also have stored files from the previous state and preloaded files. If the user scrolls to the top, we get stored files and put them in the viewport. If the user scrolls to the bottom, we move the top files from the viewport to the store. And also, we get preloaded files and move them to the viewport. Next, we begin loading the next group of preloaded files and remove old files from the store. Finally, here's a new state. Interviewer may ask us why we are not using pagination. In my particular opinion, an infinity list is more convenient in this case. However, I'm sure that using pagination would not be a mistake, since mentioning possible caveats is crucial in itself. The final topic is security. We have already discussed specific security measures for file uploading services, such as encryption. Now let's look at more general security recommendations that are beneficial for all web applications. First, we have cross-site scripting. Cross-site scripting comes in various forms, but the main idea is to execute malicious code on the client's device to perform harmful actions or steal information. To prevent this, we should sanitize all users' input before sending it to the server. The same applies in reverse. Any data received from the server should be sanitized before adding it to the document. Additionally, we should avoid using unsafe DOM methods like innerHTML. A modern approach is to prevent cross-site scripting by using content security policy and trusted types. Another potential problem is cross-site request forgery. We must ensure that only authorized users have access to files, whether they are the owners or the files were shared with them. Cross-site request forgery attempts to force a user to send a request to a target resource with an authorized session. To prevent cross-site request forgery attacks, we should employ several tactics because browser support for some techniques is not 100% reliable. The first thing is using same-site cookie attribute, the easiest and most robust solution, although not supported by all browsers. The next is using CSRF tokens, the next most reliable solution, which requires additional development and token management. And last one, we can use origin and refer headers, although origin is not supported by some browsers and refer is avoided by others for privacy reasons. The next problem is clickjacking. It's a type of UI attack where attackers create a web page with content like click to get your phone, while invisibly overlaying another page, for example, bank's account page, via an iframe. When the users click, they perform actions like sending payments to the attacker. To prevent clickjacking, we should disable our app from being used within an iframe. The Xframe options HTTP header can prevent or limit the usage of our site as an iframe. Lastly, we should ensure that we use secure connections by using HTTPS, which has become the standard for web application. Okay, let's review and ensure that we have covered all the key points. We have discussed fundamental file operations such as adding and sharing files. We also discussed browsing, sorting, and other operations, and we decided that we moved all these operations to the server side to ensure optimal performance, with the client responsible only for displaying and browsing data. Now let's address to the non-functional requirements. Our application is accessible to users with various disabilities. It's performant. We have optimized performance of our application by moving heavy computations to the server and improving network and interface performance. It's localized. We have discussed translations, formats, and the specifics of right-to-left languages. We support offline mode. Our application is available offline through service workers and the Cache API. Users can mark files as available offline, and they will be stored in the IndexedDB. And security. We have covered specific security issues for file storage, like encryption, and provided general security recommendations for all web applications. We will end up here. Throughout this video, I've tried to use an experience of real-world apps. For instance, I got information from Dropbox documentation and engineering blogs. I will include all relevant links below. If you found this video useful, please don't forget to click the like button and subscribe to the channel. Stay tuned for more videos coming soon. See you next time. Bye.